welcome. Good morning. Welcome to Build Stuff. This is, I think, the second or third slot of the day, so thank you very much for joining. I hope you're not too hungry just yet, so we'll figure it out as we go. My name is Gabel. I work for an Israeli company called Wix. We do have offices in Vilnius. Yes, we are hiring. I'm not going to mention it beyond the fact that we have a booth outside with a pretty cool kind of competitive whack-a-mole style table. So if you're curious or bored, you're more than welcome to drop by our booth. We'd love to host you. As you might expect, given the title, this is going to be a talk about dependency injection, and specifically, it's going to be sort of my attempt to revisit dependency injection, because nowadays, with modern-day software engineering, it's sort of granted that you might use some sort of dependency injection framework in your code bases. So whether you're doing Java and you use Spring, .NET, I haven't done any .NET development for 10 years, so I don't know if Castle is still a thing. Apologize for that. And even AngularJS, right, is sort of built on top of an IOC container. So all of these things are sort of ubiquitous nowadays. It's kind of hard to ignore them. And my, the idea behind this talk is for me to ask the question, is dependency injection really a valuable pattern? Is it something that is desirable? Is it something that you would want to do in your sort of modern day engineering practices? We're going to have to start with a bit of a full disclosure. I was never a big fan of dependency injection as I understood it. I did do a lot of research for this talk. I read a ton of material. I spoke to a bunch of people. I tried to sort of regain an understanding of what it's about and, why is this pattern so popular? What advantages does it give? What are the disadvantages? I really, really tried to be objective about it. And it still turned out to be a rant. So ahead of time, right? I really did try to sort of elucidate why I think dependency injection might be a good thing or a bad thing, and in which scenarios. I do have my biases. Like I said, I was never a fan. So take everything I say with a grain of salt, and think about it for yourselves a bit before you sort of deep dive into building your next software project. The next thing we need to cover is, when I say dependency injection, the thing that you're sort of probably, the image that pops to your mind is probably something like this. I'm going to be using Java for examples, not because I'm a huge fan, but because it's sort of the most, kind of accessible thing. Everyone sort of knows Java, or at least can read through the syntax, so I hope there won't be any surprises. But this is not a Java talk. This is sort of a general purpose software engineering dissertation. So the thing about that is, if that's what you have in mind, right, you have your dependency injection framework, you bind types to their respective implementations and such, and you call dependency injection, well, that's sort of what I used to do as well, and it turns out that semantically speaking, it's not actually correct. So in order to actually discuss dependency injection in any meaningful way, the first thing we got to do is discuss semantics a little bit. Before I dig into that, I want to preface this by saying that if you have any questions, if you have any arguments you want to make, feel free to raise your hand or whatever. I'll try and pause and ask you questions. There's no need to kind of be formal about it or wait for the very end for questions. So just, if you feel like engaging, engage. That's good. Right. Starting at the beginning, the D in solid. So in case you've been hiding under a rock somewhere for the last 20 years and you've never heard of the solid principles of object engineering software development, these are 5 very, very broad kind of principles that were elucidated by Michael Feathers way back when, somewhere around 2004, I think, that attempt to prescribe sort of guiding principles for modern day quality software engineering in an object-oriented space. There's a bunch of these. I'm not going to cover them at all, except that last one, which is dependency inversion. So one of the common misconceptions of people when it comes to dependency injection is that the D in solid stands for dependency injection. That is not actually accurate. It stands for dependency inversion, which is a much simpler principle underlying everything else that we're going to be talking about over the next, 40 minutes or so. Now, dependency inversion is a really simple concept. Basically, what it means is if you have two services, two components, right, two classes in your system, whatever you choose to call them, two moving parts that comprise your software system, and there's a dependency between them. So in this example, your OAuth provider might be dependent on some type of user store in order to actually, store the user data somewhere in order to authenticate. The principle stipulates that you shouldn't be depending directly on concrete implementations, right? Your OAuth provider should not be depending directly on your MySQL user store, right? This is sort of bread and butter for us nowadays. But in case you haven't run into like a concrete definition of what this means before, the dependency inversion principle stipulates that you should be depending on abstractions, right? You should, instead of relying on the projector, all right. Well, I'm gonna assume and hope that this sorts itself out in the next minute or so, and in the meantime, I'll just go on talking. Dependency inversion stipulates that you should not be depending on concrete implementations. You should be depending on abstractions. So in the case of this example, and here we go. In the case of this example, you should not be directly depending on the MySQL user store. You should be abstracting into a generic concept of what a user store is, define an API for it, and then you have your sort of bidirectional dependency in that your consumer of that service, being the OAuth provider, depends on the abstraction that is a user store, and then you have your MySQL user store, sorry about that, depending on the same abstraction and implementing it. Right? So the reason it's called dependency inversion is that when this concept was sort of elucidated for the first time in the early 90s, it inverted the way people were kind of traditionally used to thinking about dependencies in software. Right? This is ancient history nowadays. Does this come as a surprise to anyone? Is this unclear to anyone? Feel free to raise your hand, shout out, throw something at me. All good. Right. So with respect to dependency inversion, it's old hat, it's old news, right? It kind of seems obvious now, even having to sort of put it out there on a slide seems kind of ridiculous because it's a thing any software engineer nowadays knows. Well, it turns out that in 1994, it was still kind of a new thing, right? And it turns out that we've made some progress in software engineering over the last 23 years. Thank God. So Uncle Bob first came up with this concept back in 1994. Nowadays, it's sort of bread and butter. Everyone knows this. Everyone agrees to it. If you don't, then we might have some interesting debates going on. But this is sort of well understood nowadays. The next thing to consider is dependency injection. Dependency injection is a slightly different concept that builds on that first principle of dependency inversion. So if we assume solid, fully sort of solid compliant software engineering, given some dependency, right? We have our user service class, and it needs to have some user store driving it. The question becomes, what is the life cycle? What are the ownership semantics for that dependency, right? Traditionally, and by traditionally I mean the way we used to build software maybe 15, 20 years ago, the user service in this case, the depending service, would actually construct and own the instance of its dependency, right? So in effect, you might have like a new MySQL user store sort of intrinsified or inlined into your depending service. Now, dependency injection is also a very simple concept, and it stipulates a very simple thing. Services should not build their own dependencies, right? Instead, services or components that have dependencies should receive those dependencies externally, and these dependencies become state. It does not, however, say how this should be implemented. So a very trivial way of implementing dependency injection is what is nowadays sort of known as constructor injection, right? If you have a user service, it depends on a user store. You just take it in your constructor, you place it in a variable somewhere, it becomes state, right? The user service should not have anything to do with the life cycle of the user store component, which is its dependency. The reason you might want to do this, I hope, is kind of self-evident, but just to elucidate it, it helps you decouple your different components. It helps you decouple your depending services from their respective dependencies. Right? And that is a very powerful thing to have, because that means you can then just come in, replace the user store with a different implementation. Say you're switching from switching from MySQL to working on top of MongoDB or whatnot. You have a completely different implementation. You just sort of slot it in. Right? And this has nothing to do with Spring or Juice or anything that you'd care to mention. This does not require any sort of infrastructure in place. It's just a very, very simple concept. So, dependency injection is a very good thing if taken at face value. If you don't throw in a whole bunch of infrastructure to help you deal with it, it's actually a remarkably uncontested notion in software engineering, right? Probably no one is going to argue that this is a good idea. And if they do, I'd love to argue with them. Right, simply common sense. Any questions so far? Any objections? I don't see any fingers in the air, so let's assume we're all good. This is where things get a little bit unfortunate, because dependency injection, being a very, very simple concept, actually has a lot of crap associated with it in modern day software engineering. And it turns out that there's a separate, not exactly a pattern, but more of an architectural principle that comes into play. So if you've ever heard the term IOC, or inversion of control, and you could never really figure out what that means or how that differs from what you know as your dependency injection framework, well, here's what it means. It's a design principle that stipulates that whereas traditionally your code has full control, like the control flow in your program starts at some point, right? You have your main entry point, right? You have your main function, whether it's in C# or Java or whatnot. Control starts there. That's where you start working, right? Traditionally, you would build up your object graph, you would build up your dependencies, and you would start doing work, right? That is sort of the trivial way of constructing software. With inversion of control, the guiding principle is that you surrender control to some sort of framework, some sort of infrastructure, what is commonly called an inversion of control container, right? I implement my main function, I build up my Spring context, and I let it go, right? I just surrender control, and I wire things into my inversion of control container, which in turn calls back into my components that I've registered with it. Right? That is why it's called inversion of control. Instead of me being fully in control and dealing with the traversal of control flow as part of my program, I just start up this container, wire things into it, and let it do its job, and it will call me whenever is appropriate. Right? So this is also a pretty simple concept in of itself. It's not even a pattern as such. It's more like a way of doing things. And if you define it like this, in a very abstract way, it turns out that it can mean a whole lot of things, right? So your servlet containers, right, Tomcat, Jetty, whatnot, are inversion of control containers. Your plugin systems are inversion of control containers, right? Stream computing, in a sense, like if you use Storm or Spark or whatever, and you submit jobs for execution, right? The thing that has the control is the framework, and it calls into your code as needed, right? All of these are implementations of an inversion of control. And the thing we're going to be focusing on is inversion of control containers as applied to dependency injection, because this is what people generally think of when the term dependency injection sort of, pops into their mind, right? This is your Springs, your Juices, your Angular factories, your whatever. Now, if you actually consider one of these frameworks, things like Spring and Juice, what are they? Essentially, they're a runtime container that manages your components, and especially it manages the life cycle of your components and wiring your components together. Right? You start up your container, you register a bunch of stuff, you tell it what the life cycle prototype is. Commonly, it would be either producing an instance on every call or having like a singleton style component in your system, and you just let it run, right? It'll call your stuff as needed. Why would you do this, right? So I talked to a whole bunch of people. I was trying to kind of come up with a list of reasons why people think this is a valuable thing to have. And generally speaking, these are the answers, right? 4 categories of answers. People would tell you that Spring, in the case of Java, right? I'm going to be focusing on Java because that's sort of the ecosystem I know best, right? But it applies just as well to pretty much any other programming language or stack that you care to mention. People do this in order to either simplify wiring between their components, simplify testing, that is a thing that comes up on every discussion around dependency injection, and there's some fringe benefits as well, such as dynamically configuring your app. And by configuration, I don't mean sort of your, whatever, your database host names, right? What I mean is if you're using an IOC container, the structure, the configuration of the moving parts within your system become configuration, right? You can switch out components for other components as part of your application configuration. Being able to do this dynamically, right? Reconfiguring your app without recompiling, repackaging, redeploying your app is thought of as a worthwhile sort of thing to do. And finally, it makes aspect-oriented programming a much easier thing to do because you have this sort of infrastructure core component that intercepts everything going on in your system, and it can choose to wrap, pretty much anything, any instance of any component with an aspect. Now, when I say let's consider each, I'm actually lying a little bit. I'm not going to touch almost at all about dynamic configuration and AOP for 2 reasons. Dynamic configuration is kind of bullshit. No one does that, right? You are never going to go out on a production server and reshuffle your wiring or your Spring XML configuration, whatever the hell it is you're working with, on the fly and restart your server. You're just not going to do that. No one does that. It goes against the grain of everything we've learned about modern day software delivery in the last 20 years. Right? Typically, you would have your app. Ideally, you would have some sort of continuous delivery pipeline that from your push to Git through to deploying your app basically takes 1 or 2 steps where you have to click a button, right? It doesn't leave a lot of room for this. It makes no sense. I don't think anyone does this. I could be proven wrong, of course, but certainly over the last 10 years of my career, I've not even run into one instance where this is proven useful. So I'm going to ignore it outright. AOP, I'm not even going to go into. If you're doing AOP, you're doing it wrong. That is just my opinion, but I don't see any value in AOP at all. I think it's risky as hell. It's a completely separate discussion, a completely separate argument that I would love to have. So if you like AOP, we can have that fight in the hallway outside, or even go outside, in the grass and just duke it out or something. So I'm not going to be talking about these 2 things. I'm going to be strictly focusing on wiring and testing, which are sort of the 2 well understood and well reasoned about benefits of dependency injection and IOC. So, wiring. I'm sorry if you can't see it in the back, but the details don't matter at all. What we have here is a class representing some sort of application, and it builds up the relevant components. So you might have like a database access layer, you might have an event store, you might have a snapshot store if you're doing event sourcing in CQRS, you would have a clock, you would have a service, right? You have all of these different components that have to be built up and wired up together. This is wiring, right? And this is actually only slightly simplified example of actual wiring for what is at least for us, one of our core microservices on a product at Wix, right? The actual code is roughly maybe twice as long as this, but it's not significantly different or more complicated. So this is actually reasonably representative of the sort of wiring together that you'd have to do on a modern day, reasonably well-factored app. Here's what it looks like with Juice. right? So you have your my app module, it extends the abstract module, and it binds a bunch of things together, right? It binds the types to providers of these types, or to instances, or to classes that actually implement that type. And a lot of sort of the constructor wrangling, right? Figuring out the order that things have to be instantiated in, and figuring out which components have to be passed on as parameters to the constructor of sort of higher level components is done automatically, right? Well, it turns out that these two things are almost identical, right? You don't really, with any even remotely well-factored code base, you don't really gain that much from the automatic wiring that Juice or Spring or any of the IOC frameworks give you. There are exceptions to that rule, and I will touch on them later. So, for any reasonably well-factored code base, there is no real tangible benefit for automatically wiring components together. Right? Wiring is trivial. If you have 20 or 50 moving parts in your system, your wiring code ends up being like maybe 50, 100 lines of code, but it expresses intent. These are not wasteful 50 or 100 lines of code. These are the 50 or 100 lines of code that determine what moving bits and pieces actually comprise your app and how they fit together. This is not cruft. This is not boilerplate. This is the very essence of what your app does and how it does what it does, right? So it turns out that you don't really get a lot of tangible benefit because you haven't saved a lot of code, but what you did do is, as with the case of most IOC containers and DI frameworks, you've remarkably increased the startup time of your service. You have negatively affected code navigability and discovery, right? Having an auto-wiring framework wire your components together makes it a hell of a lot harder to figure out what actual implementations of what actual interfaces get created when and passed to which service. It just makes it hard. And some IDEs are better than others at helping you with that. So if you use Spring and IntelliJ IDEA, it actually has a lot of tooling in there to aid in that. Right? So if there's a bean and there's only one implementation in context, then it'll help you sort of get there. But I assert that you don't need that, right? It's much easier to just have a line of code that says, start up this component, then pass it to the constructor of the next component. It makes it easier to reason about. It makes your system that much easier to figure out coming into it like 2 months later, or having another person, another engineer coming into your code base. It makes it so much easier to reason about if things are just laid out simply with no magic going on. And then lastly, almost all of these frameworks, all of these IOC containers, whether they be in Java or in JavaScript, if you use AngularJS, actually use a lot of magic under the hood to actually perform the wiring for you. And this reflective magic, or basically any sort of late-bound dynamic wiring of components, makes it really, really difficult to know what actually goes on in your service. Right, so I would argue that there's simply almost zero benefit around wiring. You don't need that benefit, and you're giving up a lot of simplicity and a lot of coherency in your code base if you use auto wiring for no benefit at all. All right, that was an arguable proposition number one for this talk. Now, let's switch over to the other proposed benefit of dependency injection, which is testing. Now, proponents of dependency injection, people who actually like working with DI frameworks, will tell you that it aids in testing, and here's why. Here's how you test things. You bring up some sort of container, right, Spring context, whatever. You swap out the components that you don't want for mock components, and you're done, right? I hope people get the joke on the third bullet, otherwise it's lost. So basically the approach is, right, I have this system that comprises a bunch of moving parts. I want to test a small subset of it. the assertion is that it's easier to take the system as a whole and replace stuff out of it with mocks so that you can still kind of test the system as a whole, but without the undesired behavior that a lot of these components actually have in real life, and that is beneficial. I assert that what you're doing is what I like to call deconstructive testing. Now, so that you have some idea of what the hell I'm talking about here, let's have a look at a dictionary definition of what deconstruction means in terms of literature, right? In terms of English studies in this case. It's a technique of literary analysis that regards meaning as resulting from the differences between words, in bold, rather than the reference to the things they actually stand for, once again in bold, right? Doing testing this way is stupid. And the reason why it's stupid is because instead of testing the thing you actually care about, right? You have a unit or a set of units in your code base that you want to test in isolation. So instead of just doing that, you take the system as a whole and you start throwing stuff out of it so that it resembles the subset of the system you actually care about. This is an inherently silly notion. And it's silly for two reasons. First of all, it turns out that you do a lot of unnecessary work. And the second is it actually introduces a lot of undesirable sort of properties to the way you do software engineering. Let me give you an example. Suppose I want to test my MySQL event store in my event store system, right? My MySQL event store comprises two components. I have the implementation of the MySQL event store, and I have some data source. Typically, for Java, it would be JDBC. For .NET, once again, 10, 15 years ago, it would have been ADO.NET. Nowadays, it's probably linked to whatever. I'm so out of context on that, so I apologize for if I get the terminology wrong. But fundamentally, we have just these two things, right? We have the unit that I'm testing. We have the underlying infrastructure that gets me to the database. These are the things I'm interested in testing. Now, if I do testing in the Spring way, what I call deconstructive testing, I have this whole graph of a system, and this is typically a very, very simplified graph. And I have my MySQL event store and its data source sort of on the side here. Now I need to start mocking stuff out. So I need to replace a different store with a mock, and I need to, because there's a clock involved, I need to replace that with like a fixed clock for testing instead of system clock, and I need to worry about all of those things that have side effects when my test code actually runs that are completely unrelated to the thing I'm actually trying to accomplish, which is to build up and test a unit that stores events on MySQL, right? Why would I ever even have to know that these things exist in the system? Why would I ever have to think about what parts of my, full-blown set of components, full-blown component graph in my system I need to replace with mocks? Why should I care? These are not part of the problem I'm trying to solve. So I assert this is a really, really, really bad idea. This is a really bad way to go about testing things. And I find it kind of remarkable that whenever I have this discussion with anyone, usually the sort of response I get is, but how do you test your system? Well, the answer is, I build up my object graph and I test it. This is what we do as software engineers all the time, right? Why do you find it easier to start up a whole system and throw stuff out of it rather than just focusing on the things you care about? Now you have more state in your mind. It's harder to reason about the structure of your tests because there's so much stuff that's completely unrelated to the thing you're actually trying to test. If you're starting up an IOC container or a Spring context or a Juice context or whatever you want to call it as part of your tests, especially as part of your unit tests, what are you doing? Why would you ever go about doing that? That is completely unrelated to the job at hand. It makes your tests harder to reason about. You have to deal with all these subtle interactions between components that you may have known about that are sort of tangentially related to the thing you're working on, and all of these other components that are completely outside of your context but are still part of your running app because you've started up a full-blown context, full-blown IOC container. And now you have to deal with these subtle interactions and either mock them out, or you have your tests fail in very spectacular ways that are really, really hard to track down simply because you don't even realize these components are part of the equation for whatever it is you're doing. That's just a remarkably bad decision to make. Furthermore, your tests, if you do it this way, your tests no longer reflect your unit structure, right? If you have a test that tests your MySQL event store and it deals with things that are not strictly part of the signature of your event store implementation, then your tests are now confusing. Your tests don't reflect the structure of your program because they deal with all this other stuff. And possibly my strongest argument is that this leads to poor design. And here is why. If you have to reason about the units that you're testing, if the unit that you're testing, and a unit doesn't necessarily have to be a class, right? It can be a bunch of classes. It can be 3 classes that comprise a subset of your system. You're basically testing an object graph that is a subset of the full-blown object graph within your full-blown system, right? If you do that, and you do it in a way where you first start up a full-blown context, you may run into a situation where units that you didn't even realize exist are now part of your code execution flow, right? Because it's easy. Because it's really, really easy to accept something that you don't actually care about in your unit just because it makes your life a tiny bit easier not to have to construct your object graph by hand. Constructing your object graphs by hand for the purposes of testing or for the purposes of building up your full-blown application forces you to actually give proper thought to whether or not certain components even belong there. It forces you to think about the relationships between units in your system and make sure that you don't have undesirable dependencies, undesirable relationships, undesirable complexity. Right? It forces you to keep the most minimal state, the most minimal subset of the system in your head as you're writing the test, which makes the test simpler and more stable and more easy to reason about. Right? When was the last time you went into a full-blown system, found a bit of functionality that might have had a bug in it, and had an easy time tracking down where the responsibility for that particular bug lies? Right? There's obviously something wrong with access to the database. Here are the only 2 or 3 classes that can be responsible for it, and anything else is completely separate. That is a really, really hard kind of leap to do when you're debugging a system, especially one that you didn't write or that you wrote a long time ago. You know the definition of legacy code is, right? Everything you didn't write in the last 2 weeks. So if you wrote a system 6 months ago, you already don't remember why you made the decisions you made, right? And having this ability to just reach into the ether and pull in various components just makes it easier for you to make the mistake of building up a large state or a large sort of object graph of your system without meaning to, which in turn makes it that much easier, that much harder to reason about that 6 months in the future when you're actually trying to debug it or add features or figure out what the hell is going on. Right? So I would argue that doing testing this way actually leads to systems that are not designed nearly as well. Now, before I go into the exceptions to these statements, or sort of the message I'm trying to convey, are there any questions or objections that you want to raise? There's at least one hand up in the air. Yes? All right, so it wasn't a question as much as a comment that if you don't, repeating for the camera, if you don't properly abstract things like accessing external resources like databases and such, your unit tests might be slow. That is correct. I would argue that using IOC containers actually makes it harder to mock these things down the road. Right? Not having to construct the object graph by hand actually makes it that much easier for unrelated components in your system to sort of inject themselves into your test, and it makes your test slower. And that is true of unit tests as well as integration tests, end-to-end tests, whatever kind of test you care to mention. Right? So not using a dependency injection container, not using Spring or Juice or whatnot, doesn't mean you get to not abstract stuff. It actually forces you to abstract stuff in a much more sort of cognizant way. It forces you to think about the layers of abstraction, and it forces you to separate concerns much more cleanly, because you can no longer, by mistake, take in some dependency that you don't really need, or that doesn't really represent the thing that you care about. Right? Because it's easy, because it's all auto-wired. You don't have to write code by hand. That is why I think it leads to poor designs. And actually not using these things tend to make your tests smaller, more concise, more tight, and faster running. All right. There's another hand there in the back, I think.
Concerning Spring.
Yes?
Two things. First, you don't need the wiring code from the interface to the implementation. It's just one annotation on the implementation, and the rest is auto-wired. And the second thing is, in Spring testing, for unit tests, they recommend manual wiring. So it's just bad practice to spin up the whole container and do it, I agree. But that's not what Spring actually recommends.
So this was a comment in two parts. Once again, sorry, I'm repeating for the camera and probably paraphrasing on the fly. The first part of it was that you don't actually have to sort of manually bind an interface to its implementation. You can just put an annotation on the implementation class instead, or on the interface class, I'm not even sure. And it does the auto wiring for you. The other part of the comment is that the recommended practice for Spring is actually for unit tests to do manual wiring and not spin up a full-blown container. My answer is also in two parts. The first is, if you don't have this very clear distinction between the interface, the implementation, and some sort of explicit statement about what implementation fits what interface, you're missing the whole point of the abstraction. Right? It's very nice that it saves you one line of code for each of these, but actually the annotation makes your code even less discoverable, because now you have to sort of guess at what the framework would do, how it would wire, etc. I consider that to be an anti-pattern. The other part is, while it's true that Spring recommends unit tests not be wired through containers, I would assert that the same principle applies for integration or end-to-end, or basically any type of testing, right? If you don't want auto wiring for unit tests, and usually the reason they recommend this is either for startup time of your tests, or for to kind of force you to not pull in a lot of unrelated stuff as part of your unit tests because they're supposed to be small, I would argue that the same scales to any type of test. Those assertions are exactly as true for your integration tests and your full-blown end-to-end tests. Why do that in the first place? All right, I don't know if that's like an acceptable answer, but we can argue about that later in the hallway. So, before sort of diving into what might be exceptions to this rule, and I'm sorry, let me shut up my phone, which is ringing like mad, to summarize, inversion of control in the DI flavor, right? DI frameworks are a solution in search of a problem. I don't think they actually bring you any tangible benefits. Once again, unless you do AOP, in which case I feel for you, but you're beyond hope. And there is one exception to that rule, and there's a caveat to that exception. With really big code bases, right? With code bases that comprise not a few dozen, but hundreds of components, hundreds of moving parts, there might be some tangible benefit there. There's another very common description for these types of systems. Monolith, enterprise, right? It's not necessarily that these are crappy systems, but typically if you had to rebuild them nowadays, you probably wouldn't have built them as big. I suppose there are cases in which there is no other choice, in which you have to build your system sort of in a monolithic way. It's just that these use cases are getting more and more unusual and kind of rarer. Like on-prem installations of software systems is almost a non-issue these days. There are definitely use cases for that. I have not run into one of those in years. I accept that they exist, and I accept that in those cases, maybe IOC has a tangible benefit for you. But I wanna stop to think a little bit about why IOC is beneficial in these cases. Now, I've given this a lot of thought, and I've talked to a lot of people in different disciplines. Some of them are working on sort of traditional enterprise software or on-prem installations and such. I have found that the primary reason why things like Spring are beneficial in this context is because they enable a trade-off. Right? The problem is that as systems grow in complexity, and by complexity I mean the sheer scope of what they do, the number of moving parts. Right? It makes the discipline required from developers working on these systems, it doesn't make it. It increases the need for discipline. And that need for discipline does not increase linearly with the size of your system. It increases exponentially. There's a reason microservices have been so successful over the last few years, whatever you think about them, right? The reason is smaller systems are way easier to reason about, right? Even very, very, very accomplished software engineers, really good software engineers have a very hard time with very large code bases. And that's just sort of a known fact at this point, right? The level of discipline required to maintain a system grows exponentially with the size of that system. So having something like Spring or any IOC container really for those types of systems enables a trade-off. It lets you trade off the level of discipline required from your software engineers working on that system, but in turn you sacrifice coherency and simplicity and navigability and discoverability of your code base. This is why legacy is so feared. If you go into a legacy code base nowadays that is very, very large and does a lot of different things, every single thing in it might be easy to reason about, but the whole structure of the system is almost impossible to reason about because there are so many things that are, interdependent or cross-dependent, which is even worse. And it makes it very hard to navigate, from that one point in your code base that you care about to all of the things that actually apply to that use case in which you operate currently. It makes it really hard to understand how the system is constructed, what goes on where. I'm hoping this isn't news to anyone. I imagine that most people in this room have had that experience of getting into a new, very large code base and just finding it really, really difficult to wrap your head around what is going on, what is the control flow for a given use case. And having something like Spring or any type of IOC container lets you make that trade-off. You can put in way more engineers on that code base, but the coherence of the code base goes to shit, and it becomes very hard to navigate. So a corollary to that statement is if you are seeing benefit from inversion of control containers in your apps, your code base is already out of control. Right? If your system is so big that having Spring in it lets you make that trade-off, lets you bring in more engineers to add features to the system, but in turn also makes it a lot harder to reason about that system, then you already have a problem. Right? This is a good indication that you should not be investing your time in adding IOC into a system or extending that system. That is the point at which you should start breaking that system down. Right? And there's 100 different talks, including right here at Build Stuff about how to break monoliths down. It's not an easy task by any stretch, but the reason you want to do this is because humans are very, very bad at keeping large systems in their head. The level of discipline required from a developer to work on a system that is big and complex is insane. And the bigger the system is, the harder it becomes, and the fewer the software engineers that can actually handle that level of complexity. So what we do instead nowadays is we break the system down into separate concerns, and we try to deal with each concern in turn. We just call them microservices. So that is most of what I have. There's actually a sample project. So the wiring I showed you earlier actually exists in a toy implementation where I basically took the opportunity to it was for a different talk about event sourcing that's actually happening tomorrow. But I also took the time to actually show how the same system can be wired just manually. You know, good old-fashioned constructors and use and passing constructor parameters around versus how it's wired with Juice. The code samples are right here in this URL. Once again, all these slides are already available and tweeted, so you can find them. And if there are any questions or arguments at this point, I don't see any hands. Okay, thank you very much for your time. This is what I have for you. Feel free to argue with me later. Cheers.